Today I will be trying to analyze how much percent of muscle fibers does an individual use while lifting weights using physics models. But before we do that, there's a few things that we need to go through first. The first thing you need to know is that the human body has limitations for strength for the safety of the person involved. Because if you were able to lift so much weight, you would just continually tear your muscles and they would degrade over time, and eventually you would run out of energy and die. The next thing you need to know is that the body uses electrical impulses to contract and expand muscles. This allows the muscle to move and it converts electrical energy into thermal energy. On the chart that you'll see that should be coming up shortly, you'll see that the human body is only able to produce a certain amount of electricity, but muscle fibers have much more potential than what humans can produce. Now that we have that schema out of the way, we can begin with the actual analysis of how much muscle fibers does our body actually use while exercising. So my hypothesis is that if you take your energy of your 1 rep max and divide it by the energy of a set till failure, that you're going to get the percentage of muscle fibers that you're not using in your 1 rep max. The logic behind this is quite simple. If you take the amount of energy it takes you to get to failure, you should be finding the amount of energy that your body can produce for that particular lift. And if you take your 1 rep max and divide it by that number, you should find the percent of energy that you're not actually using in your 1 rep max. The easiest way to find the energy that your body is using during a lift is to use joules and use a simple formula: force times the distance parallel to the force. The force is obviously going to be the mass times gravity. This is because, as you can see by the force vector diagram, that the normal force from the person would be the same as the force going down by the weight. And the distance is going to be the distance that it is moved times 2, because it moves both up and down. This energy bar chart basically shows that the work of the person would be the same as the work of the gravity of the weight. So now that that's out of the way, how about we start analyzing some data. So what we're seeing here is Brandon Lee is lifting a mass of 45.3592 kilograms, which is about 100 pounds, and he's going to do this for about 16 reps. The distance that the weight is moving is equal to about 0.41 meters. It might be slightly off every single time, but not so much that it's going to affect the experiment much. And if you double this, I would like to note that even though he's not moving at a constant velocity, it should not affect the results of this experiment because we're using a work equation. You may also notice that the weight's not moving completely vertically. If I could change this, I would use a Smith machine, but there just was not a Smith machine available. I did not want Brendan doing his 1 rep max for this lift because it's a very dangerous lift, so instead we're going to calculate it using the Epley formula. The Epley formula is found to be the most accurate when doing reps between 12 and 18, and Brandon fell right in between this. There's other methods that are for lower reps and other methods for higher reps, but we're going to focus on the Epley formula for the sake of this experiment. So using that formula, we found the 1 rep max to be 69.5507 kilograms, which would equal 558.909 joules using the same formula. The other 16 reps would equal 5,832.1044 joules. So if we take these two numbers and plug them into the formula that I proposed at the beginning, we get the decimal 0.0958, which would equal 9.58%. So basically this means that when we do lift the most amount of weight that we can lift, we're actually lifting underneath 10% of what the potential energy our muscles have. Using this data, one could claim that our 1 rep max is actually 1/10 of what our potential 1 rep max is. And I was researching and I couldn't find any data on this subject, so I could not really compare this to anything else. But looking at some news stories, there's been old grandmas who can lift cars miraculously off their children and they have no weight training whatsoever. So I have to say that this could be an accurate number. What I did next is I used the same equation that I used for the work to find the unused percentage of muscle, and I decided to apply it to a power model. As you can see here, Brandon moves the first mass of 54.4311 in about 1 second, and he moves the second mass of 70.3068 kilograms in about 3.5 seconds. If we plug both of these power ratings into the equation, we'd find that the ratio equals 0.3690. As you can see, the percentage that we got for the power was much higher than the percentage we got for the work. If I had to guess which one was more accurate, I would guess the power, because we stayed at a more constant velocity and thus just minimizes the room for error. We get these percentages because we times each ratio by 100, because this would give us the percentage of either energy or muscle fibers being used, depending on how you depict these results. In conclusion, I can confidently say that physics does in fact prove that a human body has the capacity to lift more of a 1 rep max than was currently being done. The human body is an amazing thing, and perhaps physics can't wholly explain why we can do these actions, like lifting a 2-ton car off of an infant, but maybe it can, and maybe this is just one step closer to finding out what the human body is completely capable of.